Alright, so in this video I'm going to discuss the solutions for assignment 2. Okay. So the first problem so in this first problem we have this tree graph, okay, and the first subproblem asks whether this is a bipolar graph. Okay. So, well, first of all, the definition of being a bipolar graph is that there's no arc cycle, and since this is a tree, so there's no cycle, so there's no arc cycle. So yes, this is a bipolar graph. But for this problem, you also have to specify the polar sets x and y. So we can start from any vertex, say the root a, and we put it in set x. So the neighbors of x will be in the set y, and the neighbors of y they are in the set x, and finally the neighbors of x, once again, they are in the set y. Okay. Okay, so the next subproblem is we have to show that this matching AC and the HBE, so this is a maximum matching. So AC and BE. All right. So to show a matching is maximal, basically you only have to check if it is possible to add any more edges to the matching and still maintain a matching. So for example, if we consider the edge AB, then adding this edge to the current matching will violate the property of matching. That is, edges in the matching, they cannot touch each other, they cannot share endpoint. So AB cannot be added to the matching. So similarly, like BD, BF, CG, EH, EI, all these edges cannot be added to the matching. So we've checked all the remaining edges, and yeah, we cannot add any more edges to the matching. So this is maximal. Okay, and so the next question is to find an M augmenting path. Okay, so to do this, I'm going to redraw the graph. So this step is not necessary if you think you can just apply the algorithm on the tree, okay? Okay, so this is the same graph, okay? And the current matching M, AC and BE. Okay, so this is the current matching, and we have to find the M augmenting path. Okay. So first we have to find out all the unsaturated vertices. Okay. And then we're going to just apply like a BFS search from these unsaturated vertices. So we can start from D, okay, and so initially all the vertices in U, they are in S, okay. So we start from the vertex D, and then we'll reach vertex B. So this will be in the set T, okay. And we have to check whether B is saturated or not. So in this case, it's not, so we can further extend the augmenting path to reach vertex E, okay. And then we can check vertex E. So from vertex E, we can reach H, okay. So this immediately gives you an augmenting path because H is in T and H is not saturated. So, okay, so this is an augmenting path. Okay. But if you want to find out all the vertices in S and T, I think this is also in T. And yeah, so let's complete the algorithm to find out the complete set of S and T, okay? But at this moment, we already have this augmenting path, okay? And clearly there are multiple augmenting paths. For example, the last H in the augmenting path can be changed to the HEI. Okay, this will also give you an augmenting path. Okay. Okay, but just for the sake of completeness, let's continue the algorithm. Okay, so starting from F. We can reach B, but B is already in T, okay? And then starting from G, we can reach C, which will then lead us to A, okay? Okay, so turns out that all the vertices in X, they are in S, and all the vertices in T, they are in T. All the vertices in Y are in T. Okay, so next we can use this augmenting path to find a larger matching. Okay. So we just take the exclusive OR of the maximal matching we had and the augmenting path. Okay, and then we can get this larger matching. Okay, so next we have to show that this is the maximum matching. Okay, and we have to do this by finding a vertex cover of the same size. So to find the vertex cover, we have to find S and T. Okay, so initially F and G, they are in S because they are not saturated. So starting from F, we can reach B. Therefore, D is also in S. Okay, and then starting from G, we can reach C. Therefore, we can reach A. Okay, and starting from S, this time we cannot further extend the path from S because there's no H that is not in the matching and instant to D, so we cannot further extend the path. And for vertex A, we can go to vertex B, but B is already in a set T. Okay, so we've checked all the vertices in S, and we get ADFG in S and BC in the set T. Okay. So to find the vertex cover, we will take all the vertices in T and all the vertices in X, excluding those in S. Okay, so we get E, B, and C. Okay, so let's check whether it is a vertex cover. So to check whether this is a vertex cover, we can see that the vertices B and C, they already cover this many edges. Okay, so basically all the edges incident to B and C are covered. So the remaining edges, the edges that cannot be covered by T, are these two. Okay, the edge between E and H and the edge between E and I. But for these two edges, they can be covered by the vertex E. So yes, this is a vertex cover, and the size is 3, okay, because there are 3 vertices in the set, okay, and 3 is the size of the matching. So this shows that the matching we have is maximum. Okay. Right. So the minimum vertex cover is B, C, and E, and this is minimum because the size equals the size of the maximum matching. Okay. So basically, we have a matching and a vertex cover that have the same size. So this simultaneously shows that the matching and the vertex cover is optimal. Okay. So next we have the edge cover. So to find the edge cover, recall that given a matching, so given a matching, we've discussed an algorithm that like transform the matching into an edge cover. Okay. And the idea is to keep all the edges in the matching, okay, and we have to add more edges because in the edge cover we have to cover every vertex. So we just consider every vertex that is not saturated. So in this case, F. So for every unsaturated vertices, we will add an edge. Any edge works. So for example, F, there's only one instant edge, so we'll pick that one to cover F. And G is not saturated, so we'll pick this edge. And I is not saturated, so we'll pick this edge. Okay? So in total, we've got 6 edges. Okay? Okay. I think I've made a mistake, but yeah. So for subproblem G, my plan was to find the maximum independent set, not the maximum matching. But that's okay, because in the last subproblem, to show that the edge cover is the best, you also have to find the independent set. Okay, so recall that to find the maximum independent set, we just take the complement of the vertex cover. Okay, so the vertex cover we have is B, C, and E. So the independent set are these 6 vertices. Okay, so you can see that this is an independent set because you cannot find an edge connecting any 2 of the chosen vertices. So for example, G and I, they are not adjacent. F and H, they are not adjacent. D and F, A and G, they are not adjacent. Okay. So yeah, because this is a bipolar graph, so A, D, F, G, they are in the same set X, so in the same pi set, so they cannot be adjacent. And I think an efficient way or systematic way to check whether this is an independent set is just to check HI, to check whether H and I are adjacent to any one of the vertices in A, D, F, G. Okay, but H and I, they are only adjacent to E. Okay, so yes, this is an independent set, and the size is 6, and this matches the size of the edge cover we had. 1, 2, 3, 4, 5, 6. Okay, so basically 3 blue edges and 3 yellow edges. So we have an edge cover and independent set, and they have the same size. So again, this shows that the maximum. So this shows that the edge cover and the independent set are optimal. Okay. Okay, so the next problem is to formulate the independent set and edge cover. Okay, so the first step is always to create the variable. And in this case, because this is independent set, so we have to choose whether an edge, a vertex is chosen or not. So we'll have a variable for every vertex. So this is just called the variables according to the labels on the vertices. So we have XA, XB, XC, and so on. Okay. So the objective function is to maximize the vertices that we can choose. Okay. So this is the objective function, and the constraint is in independent set, we cannot choose two vertices that are adjacent to each other. So this means for every edge, we can choose at most one of its m points. So let's call this h1, h2, okay. So we have a constraint for every h, starting from the first one, a and b. So we have this constraint, okay? And for HE2, we have XA plus XC is at most 1, okay? All the way to the last edge, E7. Okay. The last is the binary variable condition or constraint, okay, saying that every variable can be only 1 or 0. Okay, so that's the integer program for maximum independent set. Okay, and then we have the edge cover. So for edge cover, we have to decide for every edge whether it is in the edge cover or not. So this time we'll have a variable for every edge. Okay. So because we just call the edges E1, E2 up to E7, so we have variables x1, x2 up to x7. Okay. Okay. So the constraint this time is to make sure that we can cover every vertex. So we have a constraint for every vertex. The constraint basically says that for this vertex that we are considering now, we have to choose at least one of its instant edges. So for vertex A, because the two instant edges are E1 and E2, so we have to make sure that x1 and x2, at least one of them is set to 1. So we can translate this idea into this inequality. Okay. So for vertex B, the instant edges are E1, E2, E4, and E5. So we have this constraint. Okay. So for C, this becomes x2 plus, oh no, I think I've missed an edge here. So actually we have 8. Okay. So 7, sorry. So here we have 8 constraints. Okay. Okay, so for vertex C, the constraint is x2 plus x6 is as 1. Okay. So here we have 9 constraints. Okay, so the last one is to make sure that vertex I is covered. So we have x8 is at this one, okay? So by just looking at the last constraint, x8 is at least 1, and we also have the binary constraint. So immediately we know that E8 must be chosen, okay? So in any feasible solution, x8 is 1, and similarly x7 is also 1 because, yeah. To cover H, we have this constraint, okay? Right, so this is problem, this is problem 2, subproblem B, this is problem 2. Okay, so the next problem is to find the dual problem, okay? Okay, so before you apply the procedures for primordial transformation, you have to be careful that the sign of these inequalities must be consistent. Okay? And the for maximization problem, all these constraints must be must use this less than or equal to sign. Okay. So this means we have to change sign. Okay. So this is like the first step to make sure that the integer or the linear program you have is in the standard form. Okay. All right. So here we just change the sign by multiplying -1 to both sides. Okay. Okay. So next step is to create the dual variable for every constraint. Okay. And then we can work on the objective function for the dual problem. So the objective function is just the inner product of the dual variable and the right hand side of the constraint. Okay? So this is the dual variable. And also all the variables they are non-negative. Okay. Okay. So for the constraint, we have to make sure that the weighted combination of the constraints is an upper bound for the objective function for the maximization problem. So to make sure that the coefficient of x1 is at least 3, the coefficient of x2 is at least -5, the coefficient for x3 is at least 6. Okay. Okay, so then we just have to figure out the coefficient of x1 in the weighted combination, okay, where the dual variables serve as the weights. Okay. So x1, so let's first consider x1, okay. So multiplying y1 to the both sides, in particular because all the variables only appear in the left hand side, so we only have to consider the left hand side. So the coefficient of x1, we have minus y1 plus 2y2 minus 2y3. Okay, and for the last one, there's no x1. Okay, so this is the first constraint. And for the second constraint, the coefficient of x2, we get 3y1, no, x2 in the second constraint. For the third constraint, we have plus 3y3, okay, and the last one, we have plus 2y4, okay, and the last one, the coefficient of x3, there's no x3 in the first constraint, and so the first term is 5y2 minus y3 plus 3y4. Okay, that's it.